So in today's video, we're going to be looking more at orthogonal projections in chapter 6.3. So this follows on from what we've just done in chapter 6.2, where we took this vector in Rn and we were projecting it down onto this one-dimensional subspace, we called it W, and we were seeing at what point on that line, that one-dimensional subspace, that projection actually hit. Okay, and that projection was always the closest point on that line to where y was. Okay, we're going to expand that today and generalize that. So instead of just taking this vector y in Rn and projecting it onto this one-dimensional subspace W, we now want to look at what happens if W is more than one-dimensional. Okay, so we're going to take this y in Rn, and we want to find its projection onto a subspace W of Rn. Okay, and we're going to call that again, that's going to be y hat. Okay, now if you remember as well, first thing as I just said, is that now we're going to consider W to be more than one-dimensional. And remember that we wanted to be able to write y as this projection onto W plus some other vector that was orthogonal to W. Okay, it was orthogonal to that vector u, which meant it was orthogonal to y hat. So we also want to be able to write y is equal to y hat plus z, where z is equal to y minus y hat is orthogonal to y hat, which means it's orthogonal to W. Okay. So, if you remember, we can write y in terms of this orthogonal basis. Okay, so let's say that this time y is in Rn. So if y is in Rn, okay, we're going to let u1 up to un be an orthogonal basis for Rn. Okay, so I take the dot product of any two of these vectors, it's going to equal 0. Okay, any two of the distinct vectors, it's going to equal 0. So I can write y in terms of this basis. I'm going to write y as c1u1 plus c2u2 all the way up to cnun. Okay. Now what I can do here is I can group these terms in y together. So let's say I take y is equal to c1u1 plus c2u2. I'm going to take that up to cpup. I'm going to group those together, plus my second group is going to be cp plus 1, up plus 1, and I'm going to add all these terms together all the way up to cnun. So I've kind of split them down the middle. Okay, what I'm going to say here is let u1 through up form a basis, and it's actually an orthogonal basis for the subspace W of Rn, or just whatever subspace you get out of that. Okay, you can form different subspaces depending on how you order these n u's. Okay, so if you wanted a different subspace, you would just reorder the elements and then you could group the relevant ones together to form that subspace W that you want. So U1 through UP is going to form a basis, an orthogonal basis for the subspace W of Rn. If I take that other set of U's, so UP plus 1 through to UN, what those are going to do is they land in this subspace, which we actually call, it's got a weird name. There's many different names for it on the internet. When I was in undergrad, this thing was called it was called WPERP, because of how you actually write this in LaTeX. It's actually \perp. So I learned it as that. Other people in textbooks, it's called WUptac is the name of this symbol, which is what I've come to know it as over the years. So it just depends like what textbook you look at. All this subspace is all of the vectors that are orthogonal to the vectors in W. Okay, so this thing is just the set of all vectors orthogonal to W. Okay, well, I'm in Rn, okay, at this point. W is a subspace of Rn. So all vectors that are orthogonal to W in Rn are all of these, well, all linear combinations of these remaining vectors that I have in my basis for Rn. Because remember, U1 through UN formed an orthogonal basis for Rn, which means all of these vectors are orthogonal to one another. I've taken P of them out, okay? So in order to deal with the rest of the dimensions, okay, n minus P dimensions, okay, those vectors that are orthogonal to the P vectors I've taken out are those remaining n minus P vectors. They form this kind of basis for WPERP or WUptac, okay? So the set of all vectors that are orthogonal to W and UP plus 1 through to UN are in that space because those vectors are orthogonal to U1 through UP. Okay, so what I have done by splitting Y into these two terms, okay, where I've taken one set of terms and I've summed them together plus this other set of terms summed together, okay, all of this lies in W. All of this lies in WUptac, okay? So all I have done here is, again, I have split Y into two elements, we can call them Z1 and Z2, such that Z1 and Z2 are orthogonal to one another, okay? Because I take the dot product of any of these terms and I'm going to get 0. So all I have done here by just separating them out is, again, I have separated Y, I've decomposed Y into two vectors that are orthogonal to one another. Very much the same as what I did in the previous chapter in 6.2, where I split it into Y hat and Z. And Z was orthogonal to Y hat. Okay? So you can write Y is equal to Z1 plus Z2, where Z1 was just C1, U1 through to CP, UP, okay? And Z2 is going to be CP plus 1, UP plus 1 through to CN, UN, okay? And Z1 and Z2 are orthogonal to one another. And you can say Z1 is in W and Z2 is in WUptac. Okay. So as I said, if you want to show that this thing Z2 is in W uptack, okay? Remember, Z2 is made up of a linear combination of these terms, okay? If you take the dot product of any of, well, this whole term actually, if you take the dot product of that term with any one of these terms in W, you're going to get 0, okay? Because you've started out with an orthogonal basis for Rn, okay? So you know that Z1, as we've set it up to be, is in W, and Z2 must be in W uptack. So I'm going to stick to the exact same notation. I'm actually going to kind of pull this back, and I'm going to stick to the same notation that I had in 6.2. So rather than calling them Z1 and Z2, I'm going to bring this back, and I'm going to call them Y hat and Z, okay? Just so that we're in the same notation as before, okay? Again, Y hat would be in W. This time W is just more than one dimension, okay? And then Z is going to be in that space that is orthogonal to W, okay? It's orthogonal to Y hat. Now, you can again prove this, okay? I think they have actually done a proof in the textbook for this, but it follows exactly the same as when we did the proof in 6.2. You can write Y hat as this sum of C1U1 plus C2U2 through to CPUP, okay? You can write Y hat in that way. And when we did that in 6.2, okay, it was just written as C times U, and we went ahead and found that coefficient for U. This is done very much the same, okay? When you do this and you decompose Y into these vectors that are orthogonal to one another, for any Y in Rn, you've split it into these vectors that are orthogonal to one another, okay? This time, you want to split it into this multi-dimensional subspace, W, and this other subspace that is perpendicular or orthogonal to W, okay? So Y hat is in W, Z is in W uptack. So what I'm going to do now is there is a theorem called the orthogonal decomposition theorem. And it's just an extension of what we did in 6.2. And what it shows is that Y hat can simply be written as this. Okay, where U1 through UP is an orthogonal basis for W. Okay, so we can write Y hat as this, okay? You can go ahead and prove this, okay? If it's actually, I think, on page 350 of the textbook. And what you actually end up doing is taking Y dotted with each of these entries. So dotted with U1, dotted with U2, etc. And then you rearrange the formula and you get each one of these C1, C2 through CP. Okay, so that's how they prove this thing. As I said, it's just an extension of exactly what we did for the proof in 6.2, but it is on page 350 if you would like to look at it. It's just a generalized form of what we did in 6.2, where we take the dot product of Y with each of the U's, and it actually falls out that you get each of these coefficients. Now, this makes it really easy, okay? You can go ahead and find these coefficients by taking the dot product of this vector Y in Rn with each of these basis vectors in W. Okay, and then you divide it by the dot product of each of these basis vectors with itself. Okay, and you can go ahead and you get this linear combination of U1 through UP, and that is the projection of Y onto this subspace W. So Y hat that we have here, that is the projection of y in Rn onto the subspace W of Rn. Okay, so what that means is that this point y hat that we get here is going to be the closest point to y that actually lies in W. Okay, so all you have to do, I think there is a drawing in the textbook that we'll get to in a minute. All it does is it finds, if you've got Rn, you've got the subspace W, okay? And then there is this random point y in Rn, this random vector. What this does is it finds the point that is closest to y that lands in W. And that is the projection of y onto this subspace, okay? Now, how do we find z? Well, all we have to do, we know y and we know y hat. So to find z, even though it has to be orthogonal to y hat, by construction of how we've done y hat, all we have to do is y minus y hat, and that will give us z, and it will automatically be orthogonal to y hat by construction of how we've done this. So to find z, and you will actually find that that thing is orthogonal to y hat. So if you dot it with y hat, it's going to give you 0. Okay. I'm going to do a quick example here. Okay. So in this example, we're going to let y equal 135 and u1 is going to equal 1, 3, negative 2, and u2 is going to equal 5, 1, 4. Okay, I'm going to let w equal the span of these two things such that they actually form an orthogonal basis for w. What does that mean? Well, that means that these two things span the space, they're linearly independent, and they're actually orthogonal to one another, okay? You actually know we've done this proof before. If they are orthogonal to one another, it actually means they're automatically linearly independent. But if you take the dot product of u1 and u2, you should get 0, okay? And they span this subspace of R3, we call it W. Now we want to write y as the sum of a vector in W and a vector that is orthogonal to W. Okay, so we want to write y as a vector in W plus a vector orthogonal to W. So basically we want to write y as this y hat vector that lies in W and z that lies in W up tack. Okay. So to find y hat, okay, by formulation, y hat is going to be y dot u1 over u1 dot u1 multiplied by u1. I've only got two vectors in W that are the basis for W. So that's going to be y dot u2 over u2 dot u2 times u2. Okay. So the only difference from what we had in 6.2 is that we now have two vectors that span this space as opposed to just the one u. Okay. If you figure this out, what you should get, and what I got, was 0 times u1 plus 2 over 3 times u2. I think it actually came out to 28 over 42 u2, which actually simplifies down to that, which is 2 over 3 u2. Okay, so y hat actually just depends on u2. Okay, it doesn't actually have a u1 component. Okay, so you can go ahead, figure this out, and it simplifies down to 2 over 3 u2. Now, I want to find z. Now, z is going to be y minus y hat. So when you do that, y is 135 minus y hat, when we look at it, was 2 over 3 times u2. So it's 2 over 3 times 514. Okay. If you work that out, what you should get is negative 7 over 3, 7 over 3, and 7 over 3. Okay. So go back and check your answer and see what this means for us. Okay, we'll put this all together. So y is equal to y hat plus z. Y hat was 2 over 3 times 514, which came out to, if you work that out, it's going to be 10 over 3, 2 over 3, and 8 over 3. Okay, all I've done there for y hat, we said y hat was 2 over 3 times u2, so I've done 2 over 3 multiplied by 514. Okay, and then z we've just found to equal negative 7 over 3, 7 over 3, and 7 over 3. If you add these two vectors together, okay, your top line becomes 3 over 3, which is 1. Your next line becomes 9 over 3, which is 3. And your last line is 15 over 3, which is 5. And that is exactly what y was. So these two things definitely add to y. Okay. Are they orthogonal? Okay. Well, if you take the dot product of each of these, okay, so I take the dot product, I do y hat dotted with z. What I end up with is negative 70 over 9 plus 14 over 9 plus 56 over 9, and that is 0. So what I have done here is I have decomposed y into two vectors that are orthogonal to one another. One of these vectors lies in w, okay, which was this y hat vector, because it is a linear combination of the basis vectors of w, u1 and u2. So y hat lies in w, and z, as it is orthogonal to y hat, means it must lie in that w uptack set, okay? It must lie in the set of vectors that are orthogonal to w. So y hat, that exists in w, and z exists in w uptack, okay? So it's the sum of two vectors that are orthogonal to one another. What else do we know? Y hat must be the closest point to y that actually lies in w. So y is 135. Okay. Y doesn't actually lie in this subspace w. But what we want to do is to find the closest point to y that does lie in w. And the answer to that is it's this vector here. Okay. 10 over 3, 2 over 3, 8 over 3 is the closest point to y that actually lies in w. Okay, it's the closest point such that the distance between y and w is the smallest. Okay, so now I want to look at the geometric interpretation of all of this. So what does this actually look like on a diagram? I'm going to refer you to figure 3 on page 351 just while I talk about this, just so you can look at that as I explain it, because it's much easier when you can actually see it. If we take this point y in Rn, okay, so it's any n-dimensional vector, it lands in n space. That is on page 351. It's that point right at the top, okay? So just that vector, that point, okay? That's the point y. What we want to do is to find its projection onto w, okay? So you've got this random point y in Rn, and you want to find the closest point to y that lands in w. That is y hat, Okay, now here what they have done, it's very difficult to visualize this when you're doing more than 2 or 3 dimensions, because you can't really visualize stuff in more dimensions than that. So what they have done here is they have assumed here that W is a 2-dimensional space. They have assumed that W has basis U1, U2. Okay, and U1 and U2 are orthogonal to one another. It means that you take the dot product of U1 and U2, you get 0. Okay, so they are perpendicular to one another, as you can see on that diagram. So that whole space spanned by U1 and U2. So it's going to be that X1 axis in both directions and the X2 axis in both directions, and then taking any linear combination of that. Okay, so you kind of end up with something that looks like R2. It isn't R2 because we're talking about 3-dimensional vectors here, or greater than 3-dimensional vectors. But what you are looking at here is something that resembles R2 in this greater dimensional space. I think here they are looking at R3. So they have taken this 2-dimensional subspace of R3. Okay, and that 2-dimensional subspace is spanned by U1 and U2. Now, to find that closest point to Y that lands in that plane, okay, in this case it's a plane, it's spanned by 2 vectors. What they have done is to find Y hat. It is the projection of Y onto W. So it's the projection of Y onto that space that is spanned by U1 and U2. And the way that we find Y hat is, as always, okay, it's going to be Y hat. It's exactly the same as the last example. Okay. So that is the closest point to Y that lies in W. Okay. Now, what you could think of this as, if we go back to what we did in 6.2, okay, again, Y hat, it was the projection of Y onto W. It was the closest point to Y that was actually in W. But W in 6.2 was only spanned by one vector. It was a 1-dimensional space. Okay, so we only had like this first term. Okay, there was no additional terms. So what we said was that it was the projection of Y onto the 1-dimensional space. But what we have here is the projection of Y onto the sum of a bunch of 1-dimensional spaces. So each term in Y hat is the projection of Y onto that 1-dimensional space. So if I wanted to project Y onto the space spanned by U1, it would be this term, okay? That is the closest point to Y that lands on the line spanned by U1. This term here is the closest point to Y that lands on the space spanned by U2. So what that would give you is effectively like Y1 hat and Y2 hat. Okay, so each one of those is the closest point to Y that lies on the space spanned by UI. Okay, so it's just the sum here of projections of Y onto these 1-dimensional spaces. But then we sum them together, and that is what gives us Y hat. So whenever you do this, where W is more than 1-dimensional, okay, you can think of it as though you are taking multiple projections of Y onto these multiple 1-dimensional spaces, and then you are taking the sum of those projections, and that is the projection of Y onto W. Okay. As I said, it's very difficult to imagine this, so the best way to look at it is by looking at figure 3 on page 351. They've done a really good diagram of this, which literally is exactly what I've just explained, but being able to see it. In this case, they've looked at a 2-dimensional subspace W of R3. Okay, so go ahead and look at that, and it does kind of pull this all together so you can see what has been happening. What would happen if Y is actually in W? Okay, if Y is in W, this subspace in Rn, okay? If y is actually in W, then going back to our initial formula, let's come all the way back to what we had here, okay? If y is in W, that means that it can be written as a linear combination of those p vectors that span W, which means each one of these would have a 0 coefficient. Cp plus 1 through Cn would have a 0 coefficient. They'd all be 0, which means that if y lies in W, it's its own projection. Okay, you don't need to project it anywhere because the closest point to y that lies in W is itself. Okay, because you don't have to go anywhere, you're already in W. So if y lies in W, let's come all the way back. If y is in W, then when you write y as the sum of two orthogonal vectors, where this one is in W and this one is in W uptack, then y is just going to equal y hat. Okay, there is going to be no z component to this. Okay, so that would be 0. So the projection of y onto W is just itself because you don't need to project y anywhere. The closest point to y that lands in W is itself. Okay, the next thing I want to look at is something called the best approximation theorem, which looks at y being close to W and what the closest point to y is. Again, that is y hat, but it's looking more at that kind of theory. So it's called the best approximation theorem. And what this theorem says is if we let W be a subspace of Rn, and then we take y as some vector in Rn. So we know already from what we've done so far, y hat is the projection of y onto W. Okay. So y hat is the closest point by definition. It's the closest point to y that is in W. Okay. So, because of that, if I take the magnitude of the difference between y and y hat, that is the distance between y and y hat. Okay, I've taken the difference between y and y hat, taken its magnitude. That would be the distance between y and y hat. That must be less than the distance between y and any other vector in W. But v does not equal y hat, otherwise this doesn't make sense. Okay, so the distance between y and y hat, being the magnitude of the vector that's the difference between y and y hat, must be less than the distance between y and any other point in W. Okay. This will actually be used later on when we look at some other theory. Sometimes what you want to do, and again this will come up later, is when you want to approximate y by using some vector that exists in a certain space. So sometimes you have this vector and you say, well, I actually wanted the vector to be in this certain space, but it's not. So how can I approximate that vector using a vector that is in the space that I want? That is where this comes in handy, because you can approximate y by the thing that's closest to it in that subspace that you're looking at. So you can approximate y by its projection onto W. So you can approximate y using y hat. So that's where this thing becomes useful. If you want to see a proof for this, it actually is a very, very simple Pythagorean theorem proof. So you can go ahead and look at that in the textbook. It's on page 352. It's literally going to be like a 3-line proof that uses the Pythagorean theorem to prove this and look at the distances between the two. If you are ever asked for the distance between y and the subspace W. So if you are asked for the distance between Y and W, what they're actually looking at is what is the closest distance between Y and W. Therefore, they want the distance between Y and its projection. They want the distance between Y and Y hat. So whenever they ask for that, that is what you're looking for. Okay? So whenever they ask that, you just want to calculate the magnitude of Y minus Y hat. Okay, very quickly to end this. Sometimes, okay, you'll notice throughout all of this, whenever we've done this and we've done any calculations like we did here, okay, when we started out this chapter, we said, okay, let Rn have this orthogonal basis, U1 through Un, okay? You don't actually need all those vectors. You don't need to know the full orthogonal basis for Rn. All you need is you need the orthogonal basis for that subspace W, and then all of your calculations will follow from that. So as long as you have your orthogonal basis for W, you can do all of your calculations. You don't need the full orthogonal basis for Rn. Okay? But what happens if that basis for W is not only orthogonal, but it's orthonormal? So all of the vectors in that basis are orthogonal to one another, so their dot product equals 0. But each of the vectors individually has a magnitude equal to 1. What happens? Well, if we come back to our formula that we had here, okay, to find Y hat is in W, okay? If instead we had an orthonormal basis rather than just this orthogonal basis, U1 through UP, okay, what happens to this formula for Y hat? Well, for an orthonormal basis, okay, orthonormal means each vector has magnitude 1, which means when I take the dot product for orthonormal, I'll write this on the side here, for orthonormal, if I've got the magnitude of a vector equal to 1, that actually means that taking the dot product of the vector with itself and square rooting it will equal 1. Okay? So, if the magnitude of the vector equals 1, that's what that means. Now, that must mean that ui dot ui must be 1. So, if my basis u1 through up for w is in fact orthonormal, then each of these denominators is going to simplify to 1. So my formula will reduce down for Y hat. So come down to here, okay. If u1 through up is in fact an orthonormal basis, for W, okay, then that means that Y hat, the closest point to Y that lands in W, actually reduces down to this formula. Okay, because each of those denominators is just 1 as their magnitude is equal to 1. Okay. Just, this actually comes from this exact formula. If instead you take a matrix U where its columns are this orthonormal basis, I shouldn't have put commas in there, let me quickly change that. Okay, so each of the columns of this matrix are one of the basis vectors for W, okay? And u1 through up is orthonormal. Okay, what does that mean? Well, I can rewrite this formula, okay? And I can rewrite it as Y hat is actually equal to U times U transpose times Y. So why can I rewrite this equation like this? Well, if we look at this term here, so U transpose Y, U transpose would actually be this matrix here transpose. So each one of the columns is now going to become a row. So the first row of U transpose is going to be U1 transpose, because I'm taking that column, I'm turning it into a row, and that's going to become my first row of U transpose. So my new matrix is going to be U1 transpose through UP transpose. So now U transpose Y is going to be each of these rows times the column Y. So I'm going to get U1 transpose Y plus U2 transpose Y through to UP transpose Y. Okay? Taking a vector transpose times another vector is the same thing as taking the dot product of the two vectors. So this would be U1 dot Y plus U2 dot Y through to UP dot Y. Okay, now I'm multiplying that by this matrix here. So what I actually end up with is each one of these terms times a column of the matrix U. So I'm going to get the column U1 multiplied by this term U1 dot Y, which is exactly the same as what I have here. Then the second column would be U2 times U2 dot Y, which would be the next term, etc. So this equation here can just be rewritten as U transpose Y, where U is just the matrix that is made up of the columns being the orthonormal basis for that subspace W. That is the end of this chapter. If you have any questions, please let me know and I'd be happy to help, and I'll see you in the next video.